Great. Okay. Hello, everybody. Welcome to another recorded session of computer graphics. These slides are all mine. I have no lineage to point to for these slides. Um, am I proud of that? I don't. I guess so. Yeah, I'm proud of that. Okay, so this is we're going to be talking about transformations. Transformations are something that are a very useful tool, a fundamental tool that we use a lot in computer graphics. It's a long word. T16S, I guess, would be the way some people abbreviate it. I'm not sure if that's the right number of letters, but it's a big word, and I'm going to move on to the next slide to tell you about it. But just so that the associated reading is Fundamentals of Computer Graphics, Chapter 6. So that's a good place to go to, for another take or a static text take. People have different ways of learning. So I want to motivate this. I want to motivate this topic. So our goal now in this class for the next, with our goal with a lot of computer graphics and our goal with the next programming project, raycasting and ray tracing, is to make 2D pictures from a 3D world. So in this illustration here, what we're seeing is there's an eye that's looking out through a screen, and in this screen, we can kind of imagine like directions that the eye is looking. Maybe those are rays of light, or just conceptually, those are directions that expand outward from the eye, pass through something that's like a window. So if we imagine that you're sitting in front of your computer, you're looking at your computer, there's an eye in your head, and there's a window, your computer screen is made up of pixels, and here we've got these little squares, and what's in each pixel is whatever goes, from your eye into the screen of your computer, which is a virtual world which is a window onto another world. And in that world, in this illustration, there are 3 triangles. So it's not the most interesting or exciting world, but this is, that's out there in the world. It could be anything. It could be, a lion stepping out into the sunlight for the first time, and that would be a very exciting thing to see. I don't know where the dark lion was. Maybe it was in a cave. Okay, so that's our goal. Our goal is to make 2D pictures from a 3D world. And we're going to need to get, technical. We're going to need to start, just using mathematical symbols, mathematical notation to express our ideas, because ultimately we're going to program computers which need us to give them very precise information. So in this diagram here, what we're seeing here, the transformation, is that the eye is being represented by a point E. We can see that point E. The direction, if you imagine you're standing there looking forward along standing there and looking forward facing that window, then your right hand, if you extend it directly out to the right, is the U, that direction U, that vector that's labeled U. The vertical direction is labeled V, and then the direction behind where you're looking is labeled W. And the reason it's pointed behind and not forward is that'll come up. And so what we see here, we see that the window that we're looking through, so it's parallel to the U and the V directions. The U and the V directions, the U is to the right, V is up, and that matches this window that we're looking at. So in the V direction, there's a top and a bottom to this window, so 2 V coordinates for a top and a bottom. And in the U direction, there's a left and a right. So, left, right, top, and bottom, that's defining this piece of window that we're looking at from the point of view of the eye. Okay, so to get really precise, let's look at a Cartesian coordinate system here. So we've got an x-axis and a y-axis, and we've got a little house. And there's coordinates on our house, so we can, describe the locations of each of those points. I'll point out this is a right-handed coordinate system. If you use your right hand, if you use your right hand and you take one of your fingers, you point it along X, and another finger you point it along Y, then This doesn't feel quite relevant yet. Then your middle, your third finger, in my case, my middle finger, because that's how I started, points towards me. That's the reason that W is facing backwards. So if X is to the right and Y is up, then Z is kind of going out of the page. And so we see, we have our x-axis and our y-axis, and we have some points labeled that are really the crucial points to define this little house. The four corners of the square, and then the three vertices or corners of the triangle, and two of those are shared with the square. So the question is, let's say we want to move this square around, move this house around. That's called translation. So we can translate the house, just move it. And in order to move a shape around, what we've done here is we've just added, in this case, 2 to the x and 1 to all of the y coordinates. Right, and that's just a very simple equation, but to get for any y point, to get x prime y prime, which is the transformed point. So that's this word transformation, to transform this square into this house into a translated house. The action of translation is adding a number to x and to y. So tx and ty are the x and the y coordinates of the translation direction, or the translation vector. Okay, let's reset this house. Let's think about what other kinds of transformations we might want to do. Okay, maybe we want to make the house bigger. So we've scaled the house. And to do this scaling, all we've done is we have multiplied all of the coordinates by, in this case, 2. We could also consider non-uniform scaling, so where we multiply x and y by a different amount. And that's just a different number to scale x by and a different number to scale y by. Okay, let's go back to our house. What other transformations might we want to do? Rotation. So we can rotate our house onto its side. And here, the equation that we'll use is I don't know, not immediately obvious. But it involves a cosine and sine. And okay, so I want to exit the slideshow and take you to something interactive here. So this is a Pixar in a Box Khan Academy, and we can play a little bit with some of these transformations. So I've got it open here. Okay, and what we're going to see here is a lamp, right? It's Pixar, they love their lamps. So here's a lamp, and we can kind of, let's see, we can put a scale transformation here, and we can scale the head of the lamp, right? So you see it's, getting larger and getting smaller. We can also come here to the head of the lamp, and we can translate it, in X, or translate it or translate it in Y. We can take a rotation here, and we can rotate the base of the lamp here, the arm. Attach some other rotations, and maybe we can move the whole lamp fixture around by translating it. So this is just an example of what how these transformations ultimately get used. So in the movie that Luxo Jr. that was in the Introduction to Computer Graphics lecture, this is what was happening. This is what the animation was. The animation was saying, okay, if the lamp is bouncing in, then it should be translating in X as it also translates in Y to simulate this bounce. So this is an animation, right? So doing this over time, and when the lamp was turning and looking in some direction, it's also at a rotation here. It's applying these transformations. So this is a kind of a motivation. This is one motivation for where these transformations come from. But they get used in other places as well, and that will Yeah, that will come up soon. Okay, so this, I encourage you to play with this Pixar in a box or play with this rigging thing later on. It's, it's kind of fun. Okay, so I'm going to introduce some mathematical, a different, mathematical formalism for these transformations, which is to use matrices. And the reason we'll use matrices is that it's going to provide a very convenient way to kind of unify everything all the different kinds of transformations we want to do. Okay, so a refresher here. This is a very quick refresher. So what I want to say is that in computer graphics, we make use of computer graphics is like an applied mathematics, like an applied math, where we take math that you've learned in the past, um, and or maybe you don't know. Some people come to computer graphics and this is their first exposure to any aspect of, in this case, linear algebra, where matrices are studied. Um, but when you study those math classes, it's often, it's very abstract. And we have a very specific goal here. We want to we want to simulate the world. We want to represent the world, simulate its motion, its actions, simulate seeing the world, and then, create pictures, create some visual, something that we can see. So this means that it may be a while since if you've taken linear algebra, it's a sort of prerequisite for this course, so I hope you have. But even if you've taken it, it's probably been a while since you used it, and some of these things may not be fresh. So here is matrix multiplication, and here is a 2 by 2 matrix, A, B, C, D. And here is a column vector, or a 2 by 1 matrix, X and Y. So the question, and this is the first question on the quiz, is what is the product of A, B, C, D times X and Y? So find X prime and Y prime. So I want you to do this. Great. So that's a 2 by 2 matrix multiplication, multiplying a matrix times a vector, and this may not be the way you learn to do it in linear algebra, but when I think of matrix vector multiplication, I think that the components of the vector are summing each component of the vector is multiplying that column of the matrix, and then they're being added together. So that's how I think of it. That's how I think of it. But it sounds like, yeah. So I'm glad that those of you who are watching this live were able to do that. Okay, so now our goal is going to be to write our transformations in matrix form, and this is going to allow us to do something pretty neat. That's going to allow us to come up with a unified way to represent all of our transformations. And so I want you to stop and try to figure out each matrix together. So if you're watching this, the recording of this in the future, each time you see a transformation, I want you to pop over and fill in the quiz what you think it should be. And yeah, I want you to try to work out what it could be using, what each of these transformations could be using a matrix. Also, before we go on, I want to show you this interactive visualization, the magnificent 2D matrix. So let me exit out of the slideshow before we go on and just show you this magnificent 2D matrix. So this is the letter M. It looks like a letter M, and this letter M is composed of a bunch of points. So you can see as I move my mouse over the different points of the letter M, you can see that it's filling in it's filling in the X and the Y component of this I guess 3D vector. And you can go here and you can play with the elements of the matrix and kind of see what it does. So you can see it kind of transforming this M around in different ways. So this is a pretty neat visualization. So there's a link to this under resources. So that's a fun thing to play with. Okay, so let's come back here. The first question I have is, what is the nothing matrix? So the matrix which does nothing, the matrix which just takes X and Y, and when you multiply X and Y by this matrix, you get X and Y out. So the same thing. Um, I'm going to pause the recording. Okay, so what is the nothing transformation? The transformation which doesn't affect the input. So x and y stay x and y, and that's the identity matrix, 1, 0, 0, 1. So let's go to the next transformation we were wondering about. In this case, it's uniform scaling. So what are the values of the A, B, C, and D of this 2 by 2 matrix, which will accomplish scaling x and y? Uniform scaling. So uniform scaling, where we make the house bigger, A, B, C, and D in that case are the scalar S times the identity matrix. Right, and that accomplishes exactly the action that we wanted. Okay, and how about non-uniform scaling? So something different will be scaled by x and by y. I think this one is pretty similar to the uniform scaling. So let's just, I'll just reveal this. And it's just a different number for the top left and the bottom right of this identity matrix. So it's the scale factor in x and the scale factor in y just appear separately in the matrix, and one is acting on x and one is acting on y. Okay, how about reflection? So reflecting horizontally. If you know this, go ahead and send me a message in chat, or send me a message privately in chat. Yeah. So okay. So yeah, this one might not be obvious, um, but are reflections are very reflections are like scales, but with a negative scale. So you can think of this as we scaled x by a negative value, and that's how we got x to flip without flipping y. So a horizontal reflection is scaling by -1 in x and 1 in y. And so the next one let's look at reflecting vertically. So in this case, what are A, B, C, and D? Um, when we do a vertical reflection, and this time it's very similar. It's just like with horizontal reflection. It's scaling in y. It's a -1 for the y scale and a 1 for the x scale, and that's going to reflect vertically. Okay. Okay, so now going back to rotation. So we looked at, rotation was something that we wanted to do. So how about doing rotation in a matrix? Um, yep, let's see. Go ahead and send it to me in chat if you know it. Um, yeah. So if we go, so if we go to our formula for what matrix multiplication was, x prime is equal to ax plus by. So in this case, we can see that x prime, a and b are just kind of, they directly come from substituting in what we see for that little equation on the left. So cosine x minus sine theta. So that's cosine x and minus sine theta, and sine theta and cosine theta. They just move over into the components of the matrix, of the 2 by 2 matrix. So great. So now we've done, what have we done so far? We've done nothing. We've done the identity transformation. We've done uniform scaling. We've done non-uniform scaling. We've done reflection. We've done rotation. And how about translation? Okay, so what are A, B, C, and D? For a translation matrix. A translation matrix that's going to take x and y to x prime, y prime by multiplying by A, B, C, and D. So what can we put in A, B, C, and D to translate x and y? And the answer is that it's a trick question. It can't be done. It's impossible. So uh, only linear 2D transformations can be represented with a 2 by 2 matrix. That doesn't sound convincing, but anything that you try to plug into A, B, C, and D is just not going to be able to work in general. So if you uh, yeah, if we were to if we were to say, okay, let's take the identity matrix and then let's put like the translation, let's make A 1 plus tx over x. Like you can sometimes work it out so that for a specific translation, you can make a specific matrix do only that, but it's going to be dependent on the coordinates that you use to solve it for. It's just uh, if you thought you had a good answer for this, I encourage you to write it out, um, and change what x and y are. Try to make x and y move by one. Add one to both x and y, and plug in a couple of different x's and y's, and maybe convince yourself that it's like not working out. So how about this? How about this matrix? So this matrix, if we look at it, what we've done is we've expanded the matrix from a 2 by 2 matrix to a 3 by 3 matrix, and then we've taken x and y, and we've added a 1 at the bottom, which is kind of, I don't know, kind of strange. This is called homogeneous coordinates. But what it lets us do, so what we see in the matrix is the top left, the top left 2 by 2 matrix. If we imagine that the matrix is a window and we resized it by dragging the bottom right corner and made it bigger, so the top left stays as the same as an identity matrix. It's an identity matrix, so it's not doing a uniform, it's not doing a scale, it's not doing a rotation, it's not doing any of that. And then the third column, which is this new extra column, is where we're putting the translation. And if we think about matrix multiplication as taking the columns of the matrix and multiplying each column by the components of the vector, and then adding them up, so what we'll get is we'll take the x component of our vector, and we multiply that first column, 1, 0, 0, by x. And so that's x. That's an x for the top spot. And then the 1 at the bottom is going to add, it's just going to add in that column, tx, ty, and 1. So it's going to add that to the result. And that's kind of exactly what we want. X plus tx, y plus ty is what we're going to get as a result of this. Yeah. So what are these homogeneous coordinates? So this slide, this and the next slide I borrowed from the Learn.graphics folks. So here's like a visualization of homogeneous coordinates. So we can take our xy, and you notice that xy is kind of xy is being drawn as like the horizontal plane, and w is pointing like up and out of the horizontal plane. So you can see that a point. So any point xy, we add a 1. So it's kind of like any point becomes, lives on this w equals 1 plane. All of our regular points live on this w equals 1 plane. Now, in properly speaking, homogeneous coordinates let you do a little more than translation. They're useful for some other reasons too that we'll talk about in a future lecture. So I'm gonna say something a little bit more general about them. In general, when people talk about homogeneous coordinates, what they will do is they will say a point, x and y, is identified with, it's equivalent to any homogeneous coordinate point where wx, wy, and w. So I kind of think about it as like, to keep myself, sane, I think of the xy plane being lifted up to xy1. We put that 1 at the bottom. So if the w is ever something that's not 1, mentally I should divide by w, divide all 3 components by w. Any point, scaling at any point by w in homogeneous coordinates is always the same point, because we're scaling that third one, we're scaling that 1 to a different number. So if you divide that back out, we get back x, y, and 1. In this case, translation is like a shear in x and y. Now, we didn't talk about shear transformations because I personally think that shear transformations are a kind of fictional transformation. Shear would take a square to a parallelogram and or a rhombus, and you get shear just by rotating, doing a non-uniform scale and rotating back. So I don't find shear a very intuitive. I don't find it intuitive. I don't find this thinking about translation as shear in x and y. It's kind of interesting. This slide is here. You can kind of come back and spend some time on this visualization if you'd like in the future. One thing I will point out though is that it's important to make a distinction between points and vectors. So a vector is a direction and a magnitude, and it doesn't make sense to translate a vector. A vector doesn't exist at a fixed location in space. A vector is a direction and a magnitude. So we wouldn't want it. If you're say translating a shape, you want that shape to move somewhere else, but you don't want to be adding and subtracting any components to the vector because those directions are not fixed in space. So that's when we use homogeneous coordinates, we'll put a 0 for the homogeneous component of a vector, and the effect that has is when you multiply this 3 by 3 matrix by the vector, that third column gets multiplied by 0. So it's as if translations don't exist and they don't modify the vectors. So it gives us this kind of clean way to use the same transformation matrix to points and vectors, but to be safe in knowing that we're not going to mess up our vectors. So here's a summary of 2D transformations using a matrix, and now using homogeneous coordinates. So we can go back and we can take our scaling and our translation and our rotation and make them all homogeneous coordinates. And in that case, we'll just use the row and column of, when we resize the window of our matrix, when we make it bigger, when we resize it, the equivalent of the blank canvas is using the identity matrix. So the rightmost row and column is just a piece of the identity matrix, and so that's going to keep the third component the same, keep it a 1 if it's a 1, and the same thing with rotation. Now, in general, the class of transformations which can be made by a matrix that looks like this. So these are 3 by 3 matrices where the bottom row is a 0, 0, and a 1. But now we have like 6 components to play with instead of 4. So our 2 by 2 matrix, there are 3 by 3 matrices, but we're going to always keep the bottom row 0, 0, 1. Then this class of transformations are affine transformations. So what affine transformations are these 2D linear transformations along with translations. So some properties: straight lines remain straight, parallel lines remain parallel, angles between lines and distances between points are not preserved. So distances between points are not preserved because we can scale them. So if we scale points, we can shrink things down and the distances can get larger or smaller. Angles between lines aren't necessarily preserved because we can do non-uniform scaling. So if we do non-uniform scaling, then we can take two lines that have a 45-degree angle, and we can kind of shrink that angle down or expand that angle. Ratios of distances between points on the same line are preserved. So if you have like a ruler and you mark off, the halfway point and the start and the end, and then you apply an affine transformation, that halfway point is still going to be halfway, even after the affine transformation. And products of affine transformation matrices are also affine transformation matrices. And if you'd like to verify this, what you can do is just write down 2 3 by 3 matrices in this form. So the bottom row is 0, 0, 1. Multiply them and convince yourself that the bottom row stays 0, 0, 1. Okay, so So why did we do everything with matrices? So it gave us a unified representation. So we can use the same. We can just think our transformations, whether they're scaling, rotation, or translation, are all just matrix multiplication. We just need to make the right matrix. Now, what that lets us do, so let's say we have a point, x, y, and w. Hopefully w is 1. And we can apply a sequence of things to it. We can do multiple things to it. So first we can scale it, and then we can rotate it, and then we can translate it. And each of those things is accomplished by this matrix multiplication. But matrix multiplication is associative. So that means that if we have, we're going to multiply p by s, the scale, and then r, the rotation, and then t, the translation, we can actually put some parentheses around t, r, and s, multiply the matrices in advance, so t times r times s, just compute 3 by 3 matrix multiplication, and then we will just store a single matrix M that does everything we need. So no matter how many operations you want to apply to your shape, to your point, you can always represent them as a single matrix. And so that has a nice property. I mean, as computer scientists, it's like, well, we don't need a linked list or some chunk of memory that can grow in size and shrink in. We need to keep track of its dynamic size because sometimes we want to apply more and fewer transformations. We can just always store 6 numbers for our affine transformation matrix. Yeah. Also, if we have 1,000,000 points and we want to multiply them by the same transformation matrices, set of transformation matrices, it's going to be much more efficient to first multiply the matrices together, get a single 4 by 4 matrix, and then apply that 4 by 4 matrix to all of the points rather than multiplying the point times a matrix 3 times or n times or however many. Yep. Okay. That's perfect. Something that's important to note, so unlike multiplication of scalars, matrix multiplication is not commutative. So translation times rotation times scale is not the same as translation times scale times rotation, which is not the same as rotation times translation times scale. Rotations and scales do sometimes commute. And so I encourage you to find a partner and multiply r times s and then s times r, and try to work out when those things are equal, what the conditions are to make those things equal. Yeah, perfect, perfect, perfect. So my complaint about shear earlier was that you could always do a shear by just rotating, scaling non-uniformly, and rotating back. And if you multiply that out, if you do that out, you'd get a single matrix, and that single matrix would be what many people call a shear matrix. Okay, let's look at some examples of matrix composition. So here we'll do a 45-degree. First, we'll do a scale. So we always when we multiply our matrices by points, by convention, our points and our vectors are always going to be columns, so column matrices or column vectors, and they're always going to be, and it's only possible to multiply those if they're on the right of a matrix to make the dimensions work out. So from that point of view, if we write a 45-degree rotation times a scale, a scale that's 2 in x and 1 in y, in English we read from left to right. So I'll read it as a rotation of 45 degrees times a scale, a non-uniform scale, 2 in x, 1 in y, but it's applied from right to left. So so I guess if I were trying to construct a grammatical English sentence that did this, I would say a rotation of 45 degrees that follows a scale of 2 in x and 1 in y. And so here we're seeing the scale of 2 in x and 1 in y, and here we see the rotation of 45 degrees. Okay, and here is the flip. So here is a rotation 45 degrees first, followed by a scale of 2 in x and 1 in y. And here's the shear transformation. And so the situation where the matrices don't commute is when the scale is non-uniform. If the scale were uniform, it would have commuted. It would commute. Okay, so now that we can compose our transformations, we can do things like rotate around an arbitrary point. So we don't need to rotate always around the origin. We can rotate around a point AB. So how can we do this? Well, we can first translate so that AB becomes the origin. So we will translate the point by minus A minus B. So that will take the point AB to the origin. Then we'll apply a rotation. And then we will translate back so that AB goes back to AB. So the point AB itself is unaffected by this rotation because while the rotation was occurring, AB was at 0, 0. And so 0, 0 times anything stays 0, 0. So that's pretty neat. We can also scale about an arbitrary point exactly in the same way. So translate so that AB becomes the origin, and then scale by x and sy, and then translate back. So let's go back to the magnificent matrix and then build a couple of matrices ourselves. So the magnificent 2D matrix. Right, so here we are. So now we see why this was 3 by 3. I felt a little bit of embarrassment when I first pulled this up because it was a 3 by 3 and I hadn't introduced that yet, and I thought it was going to give away the translation, how translation worked. Or just be confusing. So I kind of tried to gloss over that, but now we see why that's there, and so we can see here what happens. So what do we see here? We see what's happening in each component. So this is the x times the 1 plus y times the 0 times a 1 times a 0. That's that. This is what ends up in the x component. If we shift down here, we see that the x is scaling the entire first column, y is scaling the second column, and the 1 component, the homogeneous component, is scaling that third column, and they're being added together. So if we go over here and we add a translation by 1, we see that being added in right here by that 1 component, by the homogeneous. Hover over the dots. Something is misbehaving on this site. We can do our scaling. Rotations are a little more annoying because I don't know cosines and sines by heart other than the really boring ones like 90 degrees. Okay, but one thing that I can show you here easily is what a shear looks like. So shear is where you just put a value in the upper right corner. And so we're kind of shearing M. And so it is a linear transformation. It's a 2 by 2, and it's just made up of scaling and rotation together, as we saw. But that's what the matrix ends up looking like. Okay, so I also wanted to show you this here. So what you're seeing here is a little bit of code. This is Python just because it's there's a really nice environment for doing numerical methods, working with matrices and so on, called NumPy, numerical Python. I like to pronounce it NumPy. And so, okay, so I've made a little function that defines a rotation matrix. You give it a theta in radians, and then it just returns a matrix, which is cosine theta minus sine theta, sine and cosine, exactly like we said. A translation, same thing. It returns a translation matrix and a scale. And so we can create a rotation by pi over 4. So that's 45 degrees. We can translate, and then we can to -1, -1, and we can translate back. We can compose these. And so if we compose these together, we can see what the components look like. So what we see here, so let me plug in some different numbers here to just kind of see what we might expect. So yeah, so one thing we see here is that if we rotate by zero, if we don't rotate at all, then if we print out this rotation first, we'll see that, you know, cosine of 0 is 1, sine of 0 is 0, so we see that this rotation matrix is just 1, 0, 0, 1. It's the identity, which is what we should expect. And so if we then translate in a translation matrix, you know, with -1, -1, and then translation matrix with 1 and 1, those cancel each other out too. So then this ends up just being the identity matrix, which is what we should expect. If you'd like me to, if you're watching this live and you'd like me to try something, a scale, a rotation, a translation in some order, just go ahead and paste it in the chat, you know, publicly or privately, whatever you'd like, and I'll go ahead and try it. Some things I like to do, I'll like to show you some properties here. So let's comment out this. So let's look at a rotation by pi. So that's a 180-degree rotation. Oops. So, well, let me round this because it's showing us incredible amount of numerical precision or imprecision, as we should expect from floating point numbers, but that's to the power 10 to the -16th, so that's very small. Let's round this to 3 decimal places. Okay, so what do we see? A 180-degree rotation just multiplies x and y by both by -1. In some sense, reflections are half rotations. 2 reflections are always a rotation. Multiplying 2 reflections together is always a rotation. Okay, so let's rotate by something more interesting. So let's rotate by, let's do our pi/4 rotation again. So what do we see? We see it's, you know, 0.707. This is like this with the square root of 2, minus 0.707, and so on. This is our rotation. Now, let's rotate by -pi/4. So this will be the inverse rotation. And if we look at the inverse, I want you to look carefully at where the minus sign is. So the minus sign just changed from the upper right to the lower left here. And that's the only change. And that's because cosine of an angle and cosine of minus that angle is the same, while sine of an angle and sine of minus that angle is minus sine of the angle, which is to say that the sine, oh, this is difficult to say, the sine SIGN of an angle, you can pull it out and put it in front of the sine SIN or SINE of the angle, and that's what we're seeing here. And what that means is that computing the inverse of a rotation matrix is as simple as taking the transpose. So let me demonstrate that for you. So let's print the thing, and then let's print R times R transpose. And that should be the identity matrix second. Oh, let me round it because that's an incredible amount of numerical precision that as humans we are not interested in. And there you go, the identity matrix. So that's neat. So you can, so rotation, the transpose of a rotation is its inverse. Okay. This little code sample is up on Piazza. Let's look at 3D transformations. So 3D transformations are going to be, we're going to need an extra dimension. So we have x, y, and z, but we can use the same homogeneous coordinate trick. A 3D point XYZ becomes XYZW, and matrices become 4 by 4. But the bottom row, that fourth row, is going to be an identity row, and that's an affine 4 by 4 matrix, affine transformation in 4 by 4, an affine transformation in 3 dimensions. And all of the same properties are going to hold from 2 dimensions. So here's our basic transformation. So a point and a vector, same thing. Scaling. So in general, our non-uniform scaling now has a third component for the scale in z, and it just goes exactly where you expected. And translation, similarly, that right column was where we were storing our translation vector, and now that vector has an extra component, and there's space for it. Rotations are more complicated or more interesting. So here, if you want to rotate around the z-axis, so in some sense, that's what we were already doing. If z was sticking out of the page, out of the 2 dimensions, then our rotation around the z-axis is what we were doing. So the upper left 2 by 2 matrix here is exactly that 2D rotation matrix. And sort of similarly, if we want to rotate around the y-axis, we just spread out the cosine and the minus signs and the sine and the cosines to the relevant, to the appropriate coordinates. So we kind of have an identity row and column here for y. So we're rotating around the y-axis means the xz plane. The y-axis is perpendicular to the xz plane. So the xz plane is the plane where the rotation is happening. So only the x and the z components are affected. So from that, having said that, we would expect the y component to remain unchanged, and the identity matrix is what does that. So that's the identity row there. Same thing for the x-axis is perpendicular to the yz plane. So here's the rotation packed into the y and z components. Rotating around an arbitrary axis and angle is there is a formula, but it's not as directly obvious as rotating around the coordinate axes. The representation, which is the nicest way to think about rotations in 3 dimensions, is to just think about a rotation, an angle, the amount you're rotating, and the axis, what axis you're rotating around. That's all the information you need to create a rotation in 3 dimensions, to know what general axis it is. So it's not necessarily x, y, or z. It can be anything, but that's the information you want to remember or work with, is the axis and the angle. And then there's a formula which will give you a matrix out of that. There are other exotic representations like quaternions, which have some convenient properties, but I don't actually think they lead to, they're not intuitive. They're not necessarily some people like them and use them, and so you'll see that terminology around, but it's not a convenient representation for humans. The convenient representation for humans is the axis and the angle. So the function that I would want is a function which takes an axis and angle and then converts it to something internally, like a matrix, and then we can use our matrix multiplication to deal with our transformations in a unified way. Okay, here's a cube. So this is why we want transformations. This is one of the great motivations for wanting transformations. Here's a cube, and this cube has it's a unit cube centered around the origin. Its vertices are at 1, 1, 1 and plus and minus 1, 1, 1. And we would like to make something out of this unit cube. So unit cube is a primitive shape. It's a simple shape, easy to describe. Let's say we want to make a cube person. This is a borrowed slide. From Learn.Graphics. So let's say we want to make a cube person. I'm going to draw on this slide, and I'm going to say, okay, so we can do this with essentially a tree data structure. So, we know some computer science. We're taking a computer science class here. So we can think of a tree. And if we think of our tree, we can think of nodes as storing transformations with respect to the parent in the tree. And so the root node of the tree is an identity matrix, and there's the cube. That's that unit cube. And then we can think, well, we want to put a head on top. So let's say we'll take a cube, and we will scale it non-uniformly and translate it up. And that's what the node m head stores, is that transformation matrix. And we can do the same thing to the left arm and the right arm. And that's maybe not uh, that we haven't yet gained anything, but now let's look at the legs of this cube person. So if we can scale the cube and rotate it a little bit to make the left and the right thighs. Now we make the left and the right calves. What we can do is we can think about the transformation of the calf from the left thigh. The left calf is a further transformation from the left thigh. So the nice thing about that is that if we rotate the left thigh, the left calf, I'm sorry, I forgot to say, when we when we apply the transformation to the cube primitive that makes up the left calf, we will apply every transformation up the chain, up the tree to the root. So the cube for the left calf will be the identity matrix times the m left thigh times m left calf. And when we do that, if we make a change to the left thigh, if we rotate the left thigh, or if we translate the cube man, the center of cube man, the identity matrix, if we change that to a translation, then all of cube man's parts translate with him, and that's convenient. That keeps that keeps our cube person from tearing apart. And so that's a computer science data structure interacting with a little bit of linear algebra to give us a convenient way to represent an articulated character. And here's another example. So in general, this notion is called a scene graph. And so you can think that we have a location for Earth. And so there's some translation that takes like a cube from a unit cube. So in the coordinate system of a unit cube is located at the origin. But Earth is not, let's say Earth is not at the origin because we're modeling the entire solar system. So we have a translation matrix and maybe a rotation that transforms space to Earth. Let me work from the bottom up, actually. So let's say we have a chair, or we have a table. We have a cube on a table. So that cube, we know the size of that cube, of a unit cube, but we have a different size. We want it on this table. So let's convert ourselves to the metric system, and let's say that the cube should be 2 meters by 1 meter. So if we think that our unit cube is a unit cube in metric, then we'll apply a non-uniform scale of 2 and 1, which scales that cube to have the right metric units, 2 and 1. And now we can think of this cube. We may have many copies of this cube. It's like a study carrel, a place to store some books. And we can think, well, we have these tables, and we want the cubes to be on the table. So if the table in its coordinate system, where from the table's point of view, it's at the origin, then we know what translation we need to apply to a cube. If the cube if the cube is at its own origin. So each object thinks of itself, the unit cube is at the origin. We're all the center of our own worlds. So the cube is at the center of its world. The cube's origin is in the cube space, in the object space. The cube lives at the origin. A chair, let's say that we have a way to make chairs, for convenience reasons, every chair will think of itself as being at the origin. So every object has its own object space where it's the center of the universe, just like every human thinks they're at the center of their own universe, at least perceptually. We're at the center of our own perceptual universe. So the purpose of the scene graph is to say, well, let's take the chair and let's translate it so that it's in the same from the from the point of view of one of these tables. We can take the table and we can translate each chair so that the chair is located in the right place from the table's point of view, and the table is now the center of its universe. Now, we'll take the table and we'll translate the table so that it's in room 134 of Innovation Hall from room 134's point of view. And in room 134's point of view, it's at the center of the universe. It's at the center of the origin. And then we'll translate room 134 to the right place in Innovation Hall. Now this might be convenient because room 136 might be just like room 134, but translated. So now we can take all of the same nodes in our tree and we can duplicate them and then apply a different transformation matrix to just translate it slightly differently. And we can fill Innovation Hall with translated copies. Innovation Hall is at the center of its own universe at the origin, so we can fill it with copies of all of our shapes. And then GMU maybe has multiple buildings, maybe only one Innovation Hall, so that's fine, but GMU is at the center of its universe. We'll translate Innovation Hall to be at the right place on campus. And then GMU is not the center of the Earth, but the center of the Earth is going to want to put GMU at the right place. And the Earth is rotating, so maybe from the solar system's point of view, we will apply a translation and a rotation to the Earth. So this is called a scene graph, and this is taking transformation matrices and putting them into a tree data structure. And then when it comes time to say where the chair is in terms of the Earth, we can just apply all of the transformation matrices one after another, going all the way up to the Earth. Okay, so this is bringing us to the end of this lecture on transformations. Next time we'll talk about viewing, views, projections, and ray casting. That's kind of what's going to come up next, because we're building up the subject matter we need to do ray tracing and ray casting. So do read ahead in the book or read the accompanying material, chapters 4 and 13, and if you want a review of some math, then you can review the miscellaneous math and the linear algebra chapter.